Good afternoon, ladies and gentlemen. It is a pleasure for me that I can introduce Monika Balászová today. She's in fact in some way connected with the seminar because her bachelor supervisor was Jaroslav Haslinger, a former organizer of this seminar, and her supervisor of both master thesis and PhD thesis was Slava Fajstar, one of the current organizers of the seminar. And so she studied all the time at our faculty, and then she moved to the Faculty of Nuclear Sciences and Physical Engineering of the Czech Technical University in Prague, where is she now employed. And today she will speak about discontinuous Galerkin method for problems in time-dependent domain theory and applications. So please take the floor.
Thank you very much for the kind invitation. Good afternoon, gentlemen. So this work is based on my PhD thesis, which I wrote under the supervision of Professor Fajstar in collaboration with Dr. Jaromír Podáček at the Institute of Thermomechanics, Academy of Sciences of the Czech Republic. And I would like to start with a brief motivation. As many of you know, most of the mathematical theoretical results on solvability and numerical analysis of non-stationary partial differential equations are obtained under the assumption that the space domain omega is independent of time t. However, problems in time-dependent domains omega t are important in a number of areas of science and technology. I can mention, for example, problems with moving boundaries, when the motion of the boundary is prescribed, or free boundary problems, when the motion of the boundary is determined together with the solution of the PDEs in consideration. This is particularly the case of fluid structure interaction problems, when the flow is solved in a domain which is deformed due to a coupling with an elastic structure. And our goal was to work out an accurate, efficient, and robust numerical method for solving problems in time-dependent domains. And why did we choose the discontinuous Galerkin method as our basis? The answer is very simple, because it combines the advantages of the finite element and the finite volume method. The finite element method uses piecewise polynomial continuous approximations, therefore it is suitable for problems with continuous solutions, and it has also high order of accuracy. Finite volume method uses piecewise constant discontinuous approximations, therefore they are suitable for problems with discontinuities or steep gradients, and however they have low order of accuracy. And the discontinuous Galerkin method uses piecewise polynomial but discontinuous approximations, and therefore it is suitable as for continuous solutions as well as problems with discontinuities or steep gradients, and it has also high order of accuracy as the finite element. So my talk will have the following structure. At first, I would like to formulate a continuous problem and its discretization using the space-time discontinuous Galerkin method. Then I would like to focus on the stability analysis and very briefly on the error estimates. And finally, I would like to show you some applications of the space-time discontinuous Galerkin method. So in the first part of my talk, I will consider a simplified model of compressible Navier-Stokes system, namely the scalar non-stationary nonlinear convection diffusion problem in a bounded time-dependent domain. Sorry. Yes. So, in a bounded time-dependent domain omega t with a prescribed right-hand side G, with a Dirichlet boundary condition UD, and an initial condition U0. I would like to note that both convection and diffusion are strongly nonlinear, and we assume that the given inviscid fluxes Fs satisfy the following properties, and the function beta from the diffusion term is bounded and Lipschitz continuous. To take into account the time dependency of our domain, we use the so-called arbitrary Lagrangian Eulerian method. We define the reference domain omega 0, and we introduce a regular one-to-one ALE mapping AT from the reference domain to the current configuration. And usually it is supposed that this mapping is sufficiently regular. We will denote the points in the reference domain by capital X and points in the current configuration by small x. So if the mapping is sufficiently regular, then we can define the so-called domain velocity, which is the partial time derivative of our mapping, and the ALE derivative of some differentiable function as the time derivative of this compound function F8. The direct use of the chain rule yields that this ALE derivative can be expressed as a sum of a classical partial time derivative and domain velocity times the gradient f. Using this result, we can reformulate our problem. So we can replace simply the classical partial time derivative, which was here, by the ALE derivative and then additional convective term. If we solve non-stationary partial differential equations, then the usual procedure is to use some semi-space discretization or space discretization, which means that we discretize only the space variable and we keep time continuous. But this leads to a big system of ODEs, which can be solved, for example, by some Runge-Kutta methods, but they are just conditionally stable. Another possibility, for example, in flow problems, it is more suitable to use some implicit or semi-implicit methods, but they are low order of accuracy in time. More suitable method is the backward difference formula, which is unconditionally stable and has a higher order accuracy in time. And another possibility is to use the space-time discontinuous Galerkin method, which means that we employ the discretization via the discontinuous Galerkin method, both in space and time. So in the following part of my talk, I will focus on this kind of discretization. So we can introduce the following partition of our time interval, 0 capital T, and we can denote the resulting subintervals by EM and their length by tau m. And one of the great advantages of the space-time discontinuous Galerkin method is that on every time interval EM, it is possible to consider a different space partition. And this motivates us to define the ALE mapping separately on each time interval, which can result in the fact that the ALE mapping will be generally discontinuous in time instance Tm in the whole time interval 0 capital T. So as a reference domain, we will introduce the domain omega T m minus 1, which should be polygonal, and the triangulation TH T m minus 1 hat will consist of closed triangles K hat with disjoint interiors, and then the triangulation THT of the current configuration omega T will will be filled with triangles K, which are images of triangles K hat. And we assume that this mapping is piecewise affine in the space, continuous in the space variable, and continuously differentiable in time t. Now we can turn our attention to the discrete function spaces, where the test function and the approximate solution will be solved. First, I would like to introduce this space A, H, P, M -1, which consists of such an integrable functions on the reference domain, which are on each element K hat polynomial up to degree P. And finally, the space SH tau PQ is a space of piecewise polynomial functions in space and time. And it consists of such a functions phi, which if I are composed with the ALE mapping, then they are polynomial in space up to degree P, and they are also polynomial in time up to degree Q. I will need the following notation in the following slides. So let FH tau denote the system of all faces of all elements K. It consists of the set of all inner faces with this upper subscript I and boundary faces with this upper subscript V. And if we have an inner face, then the adjacent elements will be denoted. Play music. I don't know. Hopefully. I hope that it is okay. I don't know if somebody can.
You just try to click on these body settings with a little bit of luck.
Oh, thank you.
Yes.
So, if we have an internal inner face gamma, then the adjacent elements to this face will be denoted by K gamma L and K gamma R, so left and the right element. For boundary faces, we will have only left elements. And we will assume that the normal is always outer normal to the left element. And over triangulation, THT, we can define a broken Sobolev space, which we will denote as HK. It consists of such functions which belongs to the Sobolev space HK on all the individual elements K. And if we have a function V, then the traces of this function will be denoted as V gamma L and V gamma R, traces from the left and from the right. Their average will be denoted with this angle brackets, and the jump of the traces of V will be denoted by this square brackets. Then HK and H gamma will be the diameter of the element K and the face gamma. And finally, for a function phi, we can denote one-sided limit at the time instant Tm. And using these one-sided limits, we can define also the jump over a time interval of this function phi. So the ALE, maybe I try to. Can you please help me how to hide this?
On more, try more on the right, the very right, there's more on the black control panel. Click that, and there should be a high control panel somewhere. Yeah.
Oh, thank you. So, the approximate solution can be derived in a standard way. We choose an arbitrary but fixed time instant t from our time interval em. We multiply our equation by a test function, then we integrate over an element k, then sum over all elements, and apply Green's theorem to the convection and diffusion terms. We introduce the concept of a numerical flux and some suitable expressions mutually vanishing. And then we arrive to the following definition. We say that the function u is an approximate solution of our problem if it belongs to the space of piecewise polynomial functions in space and time, and it satisfies the following two relations. Here we have a lot of forms. I will introduce them individually. So this first term, which is not written in red, it is only the Airy derivative multiplied by the test function and integrated over the domain omega t. Then this red form, AH, represents the discretization of the diffusion term. We have here sums over the element k, sums over the interfaces, and sum of boundary faces. And the constant theta can be chosen as 1, 0, or -1, and so we get the symmetric, incomplete, and non-symmetric version of discretization of this diffusion term. Then this form GH represents the interior and boundary penalization term. Here, the constant CW should be sufficiently large, positive constant, as we will see later. And for a sufficiently regular exact solution, U, this first term is equal to 0 because the jump over the interfaces is equal to 0. And this second term with the boundary faces will be compensated in the discretization of this right-hand side form LH. Moreover, the form BH represents the discretization of BH will be represent the discretization of the original convection term. Here, H is the numerical flux, which has three important properties. It is consistent, conservative, and which is continuous. Then we have the form DH. It stands for the discretization of the additional convective term. It is just multiplied by the test function and integrated and summed over all elements. And finally, the form LH represents the discretization of the original right-hand side term, this G. And here we have the compensation for the boundary penalization. In the definition, there is one more term which I didn't mention yet. This is this term with the jump over the time instant m-1. This term sticks together the approximate solution on neighboring time intervals. So our goal was to prove that this method is unconditionally stable. And in the analysis, we used two special norms. The first is the DG norm, which is the sum of the H1 semi-norm and the interior and boundary penalization term. And the second special norm was this DGB norm of the Dirichlet boundary condition, which equals to the boundary part of the penalization term. Then we assumed that the ALE mapping and its inverse are sufficiently regular, belongs to these Bochner spaces, and also the Jacobians are sufficiently regular. And moreover, we assume that the Jacobians are bounded from below and above with suitable constants Cj minus and Cj plus. So the first step towards the stability analysis was to replace the test function phi with the approximate solution, and then we arrived to this basic identity. And our goal was to estimate all the individual terms in this equation. The proofs were so after some technical issues, we are back. And so for the sufficiently large constant CW, we proved that the diffusion and penalty term is coercive. So we get this lower bound with these two special norms, the DG and the DGB norm. Then for the convective terms and for the right-hand side, we derived these inequalities where we used again the Young inequality with this constant K1, K2, K3, and we again used these special norms DG of the approximate solution. We have here also the L2 norm, the classical L2 norm of the approximate solution, then L2 norm of the right-hand side, and the DGB norm of the Dirichlet boundary condition. And for the terms containing the ALE derivative, we used the Reynolds transport theorem and some trivial manipulations here for the jump term, and we get this equations. Here the constant Cz is from the Reynolds transport theorem, and it is also a positive constant. So if we put all these estimates together, rearrange and choose the constant from the Young inequalities properly, then we can end up with this this estimate, which is almost what we want. But there is this problematic red term containing the L2 norm of the approximate solution. So our further goal was to get rid of this problematic term and to try to estimate this term in terms of data of the right-hand side Dirichlet boundary condition and interpolation of the initial condition. So to do so, we generalized the concept of the discrete characteristic function. So if we have an approximate solution U on the current configuration, then using the ALE mapping, we can transform it to the reference domain. So we do this composed function, and we are on the reference domain. Then on this reference domain, we defined the discrete characteristic function to U tilde as a U S tilde, satisfying these two these two identities, where this lower order, lower polynomial order in time was compensated with this second equation, where we have the equality in the time instance Tm minus 1 from the right. And if we have a discrete characteristic function on the reference domain, then again using the inverse ALE mapping, we transform it back to the current configuration, and we can continue with the estimates. What was difficult on this definition to choose or to define such a discrete characteristic function which is continuous and not just in the AL2 norm, but also in this special DG norm. So we proved these two estimates, and the key was again to transform this discrete characteristic function to the reference domain. Then on the reference domain use already known estimates, and then again transforming back to the correct configuration. And finally, using the continuity of this discontinuous of this discrete characteristic function, we could estimate this problematic term with the L2 norm in terms of data. You can see here the right-hand side and the Dirichlet boundary condition and the value of the approximate solution, which is already known. So we arrived to the final result about the unconditional stability. So we have on the left side suitable norms of the approximate solution, and it is bounded with constant CT5, which is independent of the time step Tm. And we have here suitable norms of data of our problems. So we prove that this proposed method is unconditionally stable. The proof is based classically on the discrete Gronwall inequality, which leads that the constant CD5 depends exponentially on the final time t. So our further goal was to derive also some error estimates. We decomposed the error E, which is the difference between the approximate solution and the exact solution, into two parts, psi and eta, where psi is the pretty part of this error. It belongs to the space of piecewise polynomial functions in space and time due to this projection operator pi. And the ugly term is this eta, which is the remainder. So it is the projection of u minus the exact solution u. And subtracting the identities for the approximate solution and for the exact solution, and setting as a test function psi, we get this identity. And again, our goal was to estimate all of the individual terms or some groups of these terms with some estimate. And again, our strategy was the same as in the case of the discrete characteristic function. So at first we transform everything to the reference domain. There we have some yet known results for fixed domains, and again transform it back to the current configuration. And we get the following abstract error estimate, and our further goal was to get an error estimate also in terms of age and tau, where age is the space step and tau is the time step. And we arrived or we faced to a difficult open problem, have to estimate the term with the expression jump of eta on a time interval j minus 1. So we decided to skip this term from the abstract error estimate. So it means that we skip this term, and due to skipping this term, we also skip this second term on the left-hand side. So we a little bit simplified our abstract error estimate, and we further worked just with this estimate. And again, we decomposed the error to two parts, to psi and eta. And again, we transform everything to the reference domain. Then we used these known estimates for these terms. And again, we transform them back to the correct configuration, and we arrived to the following error estimate in terms of the space step and the time step. So the proofs are quite complicated, and you can find it in my thesis. And in the last part of my talk, I would like to show you some applications of the space-time discontinuous Galerkin method for the system of compressible Navier-Stokes equations in time-dependent domains. So the compressible flow problem consisting of the continuity equation, the Navier-Stokes equation, the energy equation can be written in the following compact form, where W is the state vector. We have here our density, V1, V2 are the components of the velocity, E is the energy. Then GS represents the modified inviscid fluxes. Here we have also the pressure P. This is the Kronecker symbol. And finally, RS represents the viscous terms, where this tau V is the viscous part of the stress tensor, and K is the thermal conductivity, and theta denotes the absolute temperature. Of course, this system is completed by initial and boundary conditions and thermal relations for the pressure and for absolute temperature. Concerning the dynamic elasticity system, we assume that the elastic body is polygonal domain, and its boundary is divided into two disjoint parts, where we describe the Dirichlet and the Neumann boundary conditions, and we are searching for a displacement function U, which satisfies the following relations. Here rho is the material density, CMB is the damping coefficient, PF denotes the first Biela-Kirchhoff stress tensor. Its form depends on the chosen elasticity model. F is the volume of the acting body force. UD is the prescribed displacement. GN is the surface traction. U0 is the initial displacement, and Z0 is the initial deformation velocity. So as I said, the form of the first Biela-Kirchhoff stress tensor depends on the chosen elasticity model. In case of the linear elasticity, the Biela-Kirchhoff stress tensor depends linearly on the strain tensor small e. Here the constants lambda b and mu b are the so-called Lamy parameters. And in case of the nonlinear elasticity, we assumed, or we consider, two elasticity models. The Saint-Venant-Kirchhoff material is related to the linear elasticity model. We just, instead of the linear strain tensor, assume the nonlinear Green strain tensor. And we also assume the so-called Nel-Hookian material, which is a little bit complicated form. We took this definition from the monograph of Ciala. And both the fluid flow and the elasticity problem was discretized by the space-time discontinuous Galerkin method, similarly as in the case of the convection diffusion problem, which means that we used piecewise polynomial function both in space and time, and they should be arbitrarily polynomial degree. Then how we determine the ALE mapping? We inspired by the research paper of Young and Marketplace, and we stated an artificial stationary linear elasticity problem. We seek for a vector D defined in the reference domain as a solution of the elastic static system, where we defined this artificial stress tensor tau A. And as soon as we have this vector D, then we can get the ALE mapping in the form capital X, which is the reference point, plus this vector D for each time instant t. And in the fluid structure interaction problem, the coupling of the discrete flow problem and the structural problem is realized via the transmission conditions, which represents the continuity of the velocity and the normal stresses on the common boundary between the fluid and the structure. So, for example, for the linear elasticity, we require that the Biela-Kirchhoff stress tensor times the outward normal should be equal to the aerodynamical stress tensor times the normal, and the velocity of the fluid should be equal to the first derivative of the displacement, and similarly in case of the nonlinear elasticity. At first, we tested the performance of our elasticity solver on a famous Turek-Heron benchmark problem. We considered the two-dimensional elastic beam attached to a rigid cylinder. The beam was 35 centimeter long and 2 millimeter high, and we evaluated the displacement of this control point A at the middle of the right end of the beam, represented by the mean value, amplitude, and the frequency of the oscillations. The beam was loaded by gravity, and we prescribed the same input data as Professor Turek and Heron. So you can see here a very unrealistic gravitational acceleration. So it doesn't correspond to the actual value. And we assume the water light density of this beam. So Professor Turek and Heron computed this benchmark problem with the aid of the finite element method and only for the Saint-Venant-Kirchhoff nonlinear elasticity model. We also computed the oscillations of this beam for the Newtonian nonlinear elasticity model, and we get very similar results, but I will show you just the results which we got for the Saint-Venant-Kirchhoff material. So as you can see, if we employ the space-time discontinuous Galerkin method with piecewise polynomial, piecewise linear approximation in time and piecewise constant approximation, piecewise linear approximation in space and piecewise constant approximation in time, then you can see that we even need smaller time steps to get some satisfactory results. With red, you can see here the reference results from the benchmark problem. published by Professor Turek and Hron. It is written in the form mean value plus minus the amplitude, and in square brackets you can see the frequency. So in this case, our results are quite far from the reference results. But if we increase the approximation in time, so if we use piecewise linear approximation in time, then we get very satisfactory results. You can see here that for all time steps, the results are almost the same, and we are very close also to the reference data. And if we further increase the approximation in time, so we use piecewise quadratic polynomials in time, then we get even better approximations. So you can see that the mean value is identical with the amplitude in case of the displacement U1. A little bit worse is in the case of the displacement in the U2 direction, but again we are very close to the reference data. So we assume that our linear solver is quite accurate, and then we turn our attention to flow-induced vocal folds vibrations. We consider this simplified model of human vocal tract. On the left, we have the inlet, gamma E, where we prescribe the inlet boundary conditions. On the right, which is a semicircle, it is actually much more bigger than on this picture. So on the right, we have the outlet. So the flow enters here on the right. It goes through this narrow channel between these black vocal folds, and then continues towards the right part of our domain, and it leaves the domain on the right. We assume that our vocal folds are isotropic with constant water-like density, and we assume that their domains are divided into 4 regions. You can see with 4 different colors corresponding to different material characteristics. And for the fluid solver, we employ the space-time discontinuous Galerkin method of degree 2 in space and degree 1 in time. We used the time step 10 to the minus 6 seconds, and the fluid domain was divided into more than 17,000 elements. Regarding the elasticity solver, we again employ the space-time discontinuous Galerkin method of degree 1 in space and time as well. And in the discretization of the vocal folds, we use more than 5,000 elements. For the first 1,000 iteration, we assume that the domain between the vocal folds and the structure is fixed. So we let it develop the flow, and after the first 1,000 iterations, we release the common boundary between the flow and the structure, and we solve the complete fluid structure interaction problem. Our goal was to compare the influence of the linear and the non-linear elasticity. So in case of the linear elasticity, the stress tensor depends on the strain tensor, small e. And as you see, in the case of the non-linear elasticity, it depends on the green strain tensor, which is non-linear, and it can be decomposed into the linear and the non-linear part. the influence of the nonlinear part of the strain tensor can be given by this ratio R. So if the ratio R is close to 1, it means that the nonlinear part, E star, of the strain tensor has practically no influence to the computation, which means that the linear elasticity model is sufficient. It will be depicted by white color. And if this ratio is close to 0, it means that the nonlinear part strongly takes effect, and it is necessary to use a nonlinear elasticity model. And it will be depicted by dark red color. So we get the following results. I also have a short video. From these pictures, you can see that in elements close to the boundary, both in case of the Neo-Hookean and in Saint-Venant-Kirchhoff material. So in elements close to the boundary, the nonlinear elasticity strongly takes effect, and therefore to correctly capture the deformation of these vocal folds, it is recommended to use a nonlinear elasticity model. So I hope that I can show you the video. So at first, you can see the whole fluid structure interaction. You can see that the main flow. We'll play it again. So the main flow after the vocal folds is deflected once to upward and then down. It corresponds to the so-called Coanda effect. And after the vocal folds, you can see some structures of vertices moving towards the outlet. And if we have a look to the vocal folds and to the elasticity ratio, then you can see that in the elements near to the boundary, there are some red elements which indicate that the nonlinear elasticity takes effect, and therefore it is necessary to capture. Therefore, it is necessary to use a nonlinear elastic model to correctly capture the motion of these vocal folds. So let me conclude. In this talk, I discretized the nonlinear convection diffusion problem in a time-dependent domain by an ALE version of the space-time discontinuous Galerkin method to prove the unconditional stability and the error estimates we needed a generalized version of the concept of discrete characteristic functions, and at the end I show you some applications of this space-time discontinuous Galerkin method in the case of fluid structure interaction problems, mainly in the flow-induced vocal folds vibrations. And from these results, we can see that the proposed method is robust and accurate. So thank you for your attention.
Thank you.